Hello, welcome to the video on vectors. So now that we're going to start applying our vectors, and we're going to use these in mechanics now. There are several things that they can represent. For us, I just want to kind of go through a little bit before we start. So the first thing to remember is that a vector has direction and magnitude. Magnitude is its size, which we represent by the length of a line. Direction is an angle usually from the positive x-axis. From the horizontal we measure that angle. Now a couple of things they may mention to us, like this first example, they may ask us to write something in magnitude direction form. Now magnitude direction form is basically a set of coordinates, or kind of looks like coordinates, sorry, where the first number represents the magnitude, the second number represents the angle or the direction of the vector. So in this case then, our vector given here is 5i minus 3j. I've already drawn it out. It goes across 5 and down 3, 5i and down 3 minus 3 in the j direction. And I'm just going to show then that the angle that I'm going to work out, my theta, is that angle there below the horizontal. So this vector goes across to the right 5 and down 3. So its magnitude then, remember we can write magnitude as the modulus 5i minus 3j. There we go. 5 look more like a 5. Go. And that is given by the length of the vector, which is the red line over there. Just a bit of Pythagoras there, so that's going to be the square root of 5 squared plus 3 squared, which is square root 34. Then for the direction, well, I've already shown, and my advice is to always kind of draw a diagram like I have there, just because at least there's no real kind of given way of where you should measure the angle from. It differs from place to place. WJC tend to like it from the positive x-axis, so I would always draw a diagram of my vector so that at least they know, yeah, I am on about this angle here, that's the one I've labelled as theta, that's what I'm on about. The examiner knows, okay, cool. They may specify in the question where to get the angle from, but in this case they haven't, so there we go. So I'm just going to work out that angle there again by seeing that it's a right angle triangle, and tan of that angle theta is equal to the opposite side over the adjacent side, and then theta is tan to the minus 1 of 3/5, which apparently comes out as 30.96 degrees. So in magnitude direction form then, all I need is, like a set of coordinates, magnitude first, direction second. There we go, that's that vector in magnitude direction form. Now remember that root 34 represents the length of the line there. So if we are given a vector in magnitude direction form, then we should be able to work out the I and the j component from using our SOHCAHTOA work. So just remember that sine of your angle, which you've got there, would equal the opposite over the hypotenuse. So that would be my j component over the hypotenuse, like that. So you could, if you knew the magnitude and knew the direction, so if you knew the magnitude, if you knew the direction, you could work that out there. Same then, you would use cos in order to work out the adjacent side there. But usually is to write it in magnitude direction form, and if they ask you to reverse it, then you can. Anyway, an alternative way of writing vectors is in column form, so you may see them in columns like that. 2, 3 would just mean 2i and 3j, so I don't know, something like minus 5, 3. The number on the top just represents i's, and the number on the bottom just represents the J's. They just want you to be aware of that. We don't tend to use them in WJC, but some other exam boards would. Just mean the same thing. Okay, so let's have a look at a couple of examples of how we could use these. Now in mechanics, usually what we will have to do is use them to represent forces, use vectors to represent forces. Here we go, here are two forces. The first one is going across and up to the right. The second one is going up to the left a little bit there, and they're acting on a body of mass 5 kilograms. So what you've kind of got, if you just want to know, maybe there's a body here, mass 5 kilograms. That first force there goes across 4 and up 1, so it's kind of acting in that direction. And this second force here goes to the left and up 1 as well. So it's kind of doing that. It's a lot smaller. It's not as the line won't be as long, so its magnitude will be less there. Just to let you know. So what you can do by using vectors is find out what the result of these forces are acting at weird angles, and we don't even pretty cool. We don't even really need to work out the magnitude or the direction of these things. We can work out the acceleration. Just from using our Newton's second law. So I've got these two forces, and Newton's second law says that the sum of these forces, so my 4I plus J, add my minus I plus J, should equal the mass of the object, which is 5 kilograms, times its acceleration, or the acceleration will also be a vector. So we can use vectors to represent forces. We can use them to represent accelerations. Now, mass is just a number, so that's a scalar, as we call it, and therefore won't be represented as a vector. So all I do is put all of my forces, add all of my forces vectors up, and that should equal the mass times the acceleration vector. So in this case then, I'm going to have 3I plus 2J equals 5 accelerations, and so my acceleration vector, quite simply, if I divide by 5, will be 3I plus 2J over 5. Or I could, if I wanted to, I could do the 3 in front of the I divided by 5 and the 2 in front of the J divided by 5. You may prefer them as decimals, you modern people, you. 0.6I plus 0.4 J. There we go. If you wanted to, 3/5 I plus 2/5 J. Done. So you just rearrange there, add all your forces up, would equal your mass times the acceleration vector, and you're away to go. Maybe just divide by the mass, and there we go, you've got your acceleration vector. So the acceleration is going across to the right and up a bit, not too much though. They're not very large values under the I's and J's, so we won't have a very big magnitude. The other thing we can use vectors for is to represent displacements. So displacement, again, just kind of like a path in space. What would happen then if you've got an object and it follows these 3 displacement vectors? So it's going to go 3I minus 4J, so something like that. Then it's going to go 2I plus J. Then it's going to go 5I plus 3J, so it's going to go something like that there. And I want to know, right, overall, what is that final vector after you travel along those 3? So what's the final displacement of the particle? Okay, so if a vector represents displacements, again, if I'm travelling along consecutive displacements, then all I need to do is add them all up together. So I take my 3I minus 4J, and then I chuck on my 2I plus J, and then I chuck on my 5I plus 3J, and then I see all in all, I'm going to have 3 plus 2 plus 5, that's 10I, minus 4 plus, and no J's. Oh yes, yeah, because it's going to go down 4, and then up 1, up another 3, yeah, okay. Yeah, so it'll just be 10I. So all in all, it'll just be across 10 to the right from where it started. If they wanted the distance, remember the distance, right, in this case is just 10, fine. But the distance will be the magnitude of the displacement. So if you've got a displacement vector like that one there, maybe 5I plus 3j, if you work out the magnitude of that, it will give you the distance that the thing would travel if it travels along that vector. There, yeah, I think that's it. That'll be fine. So vectors can represent forces and accelerations. They can also represent displacements for us. They are usually the more common things. You can also have them for a velocity, but we won't tend to use them in that way yet. Thank you very much.